Good morning. We'll continue with the regression estimation. So previously we investigate the bias correction, right? Regression estimator has a bias, and the bias can be made to zero if X include CI. That's it. Then we have we get internal bias correction. So that is called IBC, internally bias calibrated. Now, for the variance, we need to do tail expansion. So the random variable, so regression estimator is a function of three random variables. 1, 2, 3 random variable. So that means we need to take a tail. We can view it as a function of three random variables, and then three, right? And then take a tail expansion. First of the tail expansion. And then this tail expansion is straightforward, right? But one thing we need to be sure is that we should apply tail expansion around in the limit, right? So this three random variable has a limit, probability limit, and Hurwitz-Thompson estimator converges to the population mean, right? And so this will converge to X bar. This will converge to Y bar. This will converge to beta, whatever the population quantity. So the Taylor's expansion, and then these quantities are not random. They are basically not random, right? This is not random. This is rather this is a finite population quantity. So then you don't have to worry about expectation. It's not random. So so then since you have a three component, we need to apply tail expansion one by one. So first part is with respect to Y. So if you, by the way, what is the form of FABC? So FABC is B plus X bar minus A times C, right? Because of this form, basically, right? If you put A equal to X bar, so A comes here, right? So it's X bar, Hurwitz-Thompson. So this is X bar Hurwitz-Thompson, Y bar Hurwitz-Thompson, right? Beta hat Hurwitz-Thompson, and something like that. So that means this is indeed, so we should understand this. We should figure out the specific form of the function, right? Analytically, so that we can apply the Taylor expansion explicitly. So that means if you apply Taylor expansion with respect to A, right? The first derivative, okay, right? This is actually with respect to B, right? So the first derivative, this is B, with respect to B is just one, right? So that means this is one. Same way, if you look at this one, with respect to A, right? So the first derivative with respect to A is actually minus C. So minus C here is a beta. No hat, just the beta, right? Beta n, minus beta n. And then third one, which is with respect to C, is X bar minus A, but A, what is A? A is the limit of X bar. So that is the X bar. So X bar minus X bar. which is 0. Okay. So that means you have the so that means this guy is this guy. No, actually no. Sorry. This guy is what? Is y bar minus x bar minus x bar b beta, right? And so which is y bar? So this is just this one. And then this guy is this guy. Okay. And then this guy is this guy. So that is your Taylor, the result of the first order Taylor expansion. And then you have a cancellation, right? Okay. So that means you obtain, right? You obtain this one. So ignoring, so I just write this Taylor expansion first, express the first order Taylor expansion, then we get this one. Okay. So then basically this nonlinear random variable, right? Nonlinear estimator becomes a linear, approximate by a linear, right? Linear estimators. So then so computing the bias, right? Computing the bias of the regression estimator is a difficult, very difficult problem. But because of this approximation, we wanna instead of computing the bias of this guy, we wanna compute the bias of this guy. Okay, so the bias of this guy is x bar minus, right? Y expectation y hat Ruby Thompson. So Ruby Thompson beta n minus. So actually, so if you take the expectation of this guy, you will get 1 over n equal to 1 to n yi minus xi prime beta. And this is 0 if this one holds, right? So you can actually get unbiased estimator anyway. And then, so that means you can obtain this. Okay, well, we haven't really discussed the bias actually at this point. We just here we just I guess here we just want to write this one as this one. And this is from 6 to 7. We just use this equality, this property, okay? And then the expectation of this guy is equal to approximately equal to expectation of this guy, which is 0. Because this one is equal to, so expectation of this is equal to yi minus xi beta, right? And that is 0 on the this by this property. Second property is the variance, right? Variance, so the variance, so we have this one, but variance, this is constant, so it doesn't matter. So the variance is just the variance of the orthogonal estimator of the residual. And so our variance estimator can be this one. So let's try to understand what is the meaning of this variance on the simple random sampling. So in the simple random sampling, basically, so this, if I write this one as a EI, right? If I write this EI, then my variance, right? My variance is the Hurwitz-Thompson estimator of the total of EI, right? And so I can use the formula for variance estimate. I can use the formula for the variance of Hurwitz-Thompson estimator on the simple random sampling to get. So remember, what is the variance formula of Hurwitz-Thompson estimator? It's this one, right? And this guy is usually is this one originally. Square. And now if I plug in this guy to here, right? If I plug in the second term, E bar population N is 0. Okay. And so that means this whole thing is becomes this. If I plug in. So in the if you're familiar with the regression, right? Regression analysis, this is essentially the sum of square of the residual, mean square error of the residual. And so you can see that you can actually decompose into sum of square total is sum of square due to regression and sum of square due to error, right? And so that means your regression estimator variance is only this part, not this part, right? So this is actually SST times R square, and this is SST times 1 minus R square. So that's why you get this one. So in the asymptotic sense, because R square is always less than or equal to 1, so that means your regression estimator almost always improves the reduces the variance over uh, over the original Hurwitz estimate, which is very attractive, right? You can by doing this estimation, you can do better. So there's no reason not to use regression estimator. And if the correlation is high, correlation is really high, right? Suppose perfect correlation. That means you get 0 variance. Surprisingly, but which makes sense because we know that regression estimator satisfies this calibration, right? So if yi indeed is really a linear function of x, right? So that means there's no error, suppose. Then this one implies, so this one with this one, right? Implies that your regression estimator yi is equal to the population total of yi. So that means your estimator is actually perfectly estimate the right accurately estimate the population total. So that means 0 variance. So which is really good. Okay. So some remark. The regression estimator, generalized regression estimator is motivated using a generalized regression model and a surface condition under the surface condition for IBC, which is in our case is xi prime lambda equal to ci, right? Under this condition, uh, the validity, the synthetic unbiasedness of the regression estimator does not depend on whether the model uh, holds or not. Right? So unbiasedness does not really need a model. So, but if the model is good, that means what? Your error will be small, right? Your error will be small. This will be small. So the variance reduction will be high. So that means your the variance of the Gregg estimator will be small if the model is good. So model is not used to justify the regression estimator in terms of bias. Rather, it is used to get a smaller variance. So the model, we use model, but it's not really model dependent. Rather, it's model assisted. So it is called model assisted, not model dependent. So model dependent means unbiasedness uh, requires model assumption. But Gregg estimator is not, right? Gregg estimator is not. So for example, for example, if your estimator is more like a beta hat plus, so your so when you create construct a regression estimator, our estimator uses the Horowitz-Thompson estimator here, something like this, right? So, but if I don't use weight, so suppose I have another estimator using the OLS. This is also, so then the new estimator y bar star is x bar prime beta hat star. So if I use this estimator is a model based. So if the model is true, then this is unbiased. Okay, but this is not model assisted because if the model is not true, then unbiasedness is no longer guaranteed. So that is the a key idea. Okay.
I understand. So this model assistance means the IBC, right?
IBC, that's a good question. So IBC is a sufficient condition for to get unbiased estimate. So that means sufficient condition, right?
So it's not like necessary.
It's not really equivalent, but one way, right? One way of doing. So instead of so instead of making IBC, if you directly use this estimator, for example, right? If you directly use this estimator, you don't have to have a IBC condition, but still unbiased. So that is good. Let me quit recording because I'm why